we're getting to a point where we're going to be moving away from having to do a lot of rote calculations. And we're going to be moving towards just straight up analysis, which is good and bad. For those of you who like computation, then it's sort of disappointing. But for those of you who absolutely do not like computation, then it gives you the benefit of being able to kind of switch gears and tackle some aspects of statistics that are kind of more real world-ish, right? Because if you think about it, whether it's individuals who work in the stock market or nurses, doctors, teachers, whatever career path you can think of, people analyze data all the time. People don't whip out a graphing calculator all the time. Right? People don't whip out a Desmos calculator even. What we want to do is we want to get to a point where we are comfortable and fluent in being able to evaluate situations numerically, yeah, but also to draw conclusions, meaningful conclusions from the information that we're given, right? So that's kind of, more than kind of, that's exactly where we want to be. And I'll talk to you a little bit more about how the third unit is going to progress. We already got started a little bit, but there's alternative forms of assessment available in this unit. Because I know some of us would prefer a pencil paper test, and some of us are more project oriented. This unit sort of lends itself more towards a project more than any other unit of study that we've had, right? Or topic of study, I should say. There's only been 2 units. So I'll get into that a little bit more, and you'll see it's good news. It's not bad news. So what we're going to do is you'll go into Blackboard. I go into my Desmos calculator, or you could go into Remind and do it that way. But you want to call up the areas under the normal curve. So what I did was I developed this script to give you the area under the curve, and so I use folders to kind of designate things. So we tackled the one part of it where we find the cumulative probability. So going back to like number or everything on the previous page, all these questions where we're asked to find the areas, that was easy enough based off of the cumulative probability component. So I can close that folder, hit that little triangle thing to close the folder. The other one I didn't organize into the folder. I just used the folder as a title, just, kind of separating, because it was like there's only 2 things, so it doesn't really need to be segmented off. But last class, what we did was we looked at problems where we had to come up with a z-score given an area, and we ran into the issue of, do we do this by guess and check? And we could, but there was a better way to do it, right? And that better way is to use the slider approach. So we have the inverse CDF of the normal distribution, right? That's what this notation is telling me, all right? So what we're looking at is a z-score corresponding with a given area, all right? The thing is, I didn't set it up so that it matches with the normal curve. So if this diagram is too distracting, then you can just tap on this guy and just shut it down. There is a way to do it, but it's really not necessary. So what this does is it gives you a z-score. Now, what you can do if you want is you can just annotate this any way that you want. Like, for example, if you wanted to make a little, like maybe it's not clear enough the way I have it written here, and you want to make an adjustment, you can put in a little note here saying gives z-score. Something very simple. And then drag that up and make that the title for the inverse CDF normal distribution from 0 to 1. All right, that's up to you. right? So, but little reminders to yourself. But what we're doing here, when we look at numbers 1 and 2, instead of guess and check, I can slide my slider to a 0.9 if my fat fingers will let me do it, and it'll spit back the appropriate z-score. Now, we did it by guess and check, but it actually turns out that even, you know, the calculator agrees with us that our guesses and checks were actually pretty solid. So probability that z is less than 1.282 is equal to 0.9. Ultimately, what we were looking for here was the 1.282. Desmos agrees with our guess and check. All right. We do the same thing with a 0.75. Slider onto the 0.75. If you have too much trouble getting there, then you can just type it in, you know, just tap on it and type it in. But for the cleaner values, it's actually pretty easy. So this one ends up being, if we round it appropriately, that is not a pen. Probability that z, let me bring it in a little bit. Z is less than 0.674. If we go 3 significant digits, it ends up being about 0.674. So that guess was our actual winner. That ends up being 0.75. All right. So it's area to the left, but ultimately it's this number again that we're looking for. All right. Then this was the question that I didn't like, but for part 2, question number 2, it says find the score separating the top 25% from the bottom 75%. There's a couple layers to this. So if I mark off where I think 25% on the high end is separated from 75% on the low end. So here's 0.75. Let me get a white marker out here. All right, so this part of it would be 75.75 or 75%, however you want to think of it. Again, what I'm looking for is a z-score. All right, so first thing I would tackle is the probability z is less than some number. Don't know what that number is. That has to amount to 0.75. Good news is we already figured that out. It's still a standard normal curve. All right, so 0.75 corresponded with a z-score of 0.674. So I'm going to pop that in right there, 0.674. But what I want to do is convert this to an x value. All right. Now, there's a couple of ways to handle this. One way would be to take my z-score formula. And, you know, we have it written down here, x minus mu over sigma, x minus x bar over s, value minus mean divided by standard deviation, essentially. But we're saying x minus mu over sigma. All right. So what I can do is I can pop in the 0.674. And the mu, which is 143, and the sigma, which is 29. All right. So then I can cross multiply. All right. So put that 0.674 over a 1. Some people like to convert that to a fraction. They're kind of a small segment of the population that like to do that, but there are some. All right. So I would do 0.674 times 29. So we have x minus $1.43 is equal to 19.546. And then I would add on the 143. And I would get a result of 162.546. Now, again, I'm not overly thrilled with, my choice of problems here. Again, 20 years ago, I just grabbed the problem from a textbook and I said, "Ah, looks good, just throw it in there." Now I'm kind of looking back and being like, yeah, I probably could have been a little bit more sensitive in terms of, what kind of problems I selected. But in the context of this question, what it's saying is that 75% of the population of women have weights that are below 162.546. All right. So I'm just digging myself deeper here, because now it's like, well, you want to change the problem, why not change the problem? All you're doing is talking about it and making us feel bad. It's not the intent. I don't like where I'm at right now in terms of this kind of question. So I did appreciate the typo bonus, the folks who submitted suggestions to change the problems. And if you come across any other problems in my packets, because even the year 2000, the year 2005 to 2010, a lot of the stuff, I mean, if you really think about it, the year 2000, which is a long time ago, that's when I started teaching, when I graduated college. That was like, I don't want to say 10 years, but like 7 or 8 years before the first iPhone came out. Like, the world was a different place, so in a lot of different ways. So if you come across a problem in my packets that you look at and say, "Oh, this is really dated," and it doesn't even have to be like inappropriate, but like just like old, like a problem where I'm referencing, I know I had a problem related to football, and it had to do with like the 2002 season. And it's like, come on, we could do better than the 2002 season. Unless we're comparing it to something more modern, it's a little dated. So find problems like that could use a little update, and I'll give you a bonus for that. And I'll follow the same claim or the statement that I made last time. 1 point for finding it, and 1 point for taking the time to revamp the problem to make it a modern type of problem. All right. So all that little soapboxing aside, we want to get to a point where we can look at this and say, all right, we don't want to do the algebra, but we want to learn from the fact that we had to do the algebra once. Maybe that'll help us with the Desmos. All right. So if you look at what we had here, and just looking at my Desmos calculator, 0.674 times 29 plus 143. That's what gave me this number. All right. So I'm just going to jot it down here. 0.674 times 29 plus 143. That's what X ended up being equal to. Now, if we put that in general terms, right, something that we can kind of build off of and use repeatedly over and over again, I guess that's the definition of repeatedly. The 0.674 was the z-score. The 0.29 was sigma, and the 143 was the mu. What that tells me is that if I get the product of the z-score and sigma and add to it mu, then that'll give me an X value. Pretty solid, right? So what we can do is go back to this computation here. And this is completely optional, which is why I didn't include it. Throw in a little z equals. So then maybe you don't even need to have that statement where it gives the z-score. But what this will do is it'll save whatever number you come up with as z. All right. So if I need the mean and the standard deviation along with that z-score to give me an x value, I can ask my user, the person who's using my Desmos, to indicate the mean and the standard deviation. So what I would say is solve for x. We need the mean, all right? So I would even elaborate on this. We need the mu and sigma. All right. So what I'll do is I'll create a relation. Oh, I don't have the add-on built in for this, but so I'll just kind of have to deal with it for now, but I'll change it later. I made that promise last time too, so here we are. There is an add-on. I mentioned this last time for computers that allow the word mu to translate into the symbol mu, right? But what you can do is just Google special characters. Desmos. Click on that or tap on that, and you see it gives you a list of copy pastable items that you can just kind of snag and put into your own Desmos, right? So that's kind of the workaround if you don't have the add-on. The issue is just like every other app enabled whatever, it's I'm sorry, touchscreen enabled app. It doesn't always do simple things like copying and pasting and stuff like that. But so what I'll do is I'll just say, for now, I'll change it later. X equals Z, which we've already established, times sigma. So in the absence of a sigma, I'll just use a capital S for now, and then later on I'll change it to a sigma before I send it out to you all. So to answer the question that will be asked, yeah, I'm going to send this out to you. Also, the updated version. All right. So all on sliders. I like to have the sliders come before my my computation. That's personal preference. If you don't care about that, then that's okay too. But then what I can do, I got my Z in there. I can manipulate my sliders. The sigma, my sigma value is 29. If you tap on it, it allows you to change the range. You can make that whatever you want. Sigma values have to be 0 or positive. So I'll make it go from 0 to I'll go 1,000. And just pick some large number, just so you have a lot of wiggle room when it comes to sliding your slider. Right? And in terms of a step, if you leave it blank, Desmos decides what the step ought to be. So that's fine. For your mean, your population mean, you want means can be negatives. So let's say negative 1,000 to 1,000. And again, just leave that as is. So now I have a lot of wiggle room when it comes to the slider. The thing is, the larger the number, the harder it is to kind of get it onto the value you want. So you'll find yourself for the more precise values, just tapping on it and typing it in anyway. But getting your parameters set up the right way is a good thing to do. All right. But then once I do that, you can see here, I got my sliders at 29 and 143 respectively. Well, I lost that. Let me just do that real quick. And you can see that it automatically computed the X value for me. All right. So for a problem like this, I got a lot of stuff going on here. Area under the normal curve. All right. If it gets too messy, then close the folder that it's in. If you want to include something in a folder, you see what I'm doing here? I grab it and I drag it up. You see how that vertical line appears? There's no vertical line next to the P, but now as I slide it up, a vertical line appears. What that does is it puts whatever gets the vertical line in the corresponding folder. So now I have that P going in the folder along with all the other stuff. All right. So that's something to keep in mind. All right. So, but yeah, that's up to you. What is this? I had a lot of extra crap here. Oh, I had an alpha. Interesting. Well, that's garbage. All right. So I want this to come along. The z-score I want. But then I can, like I said, I can close the folder, and now the only thing that appears is this stuff. If you want to, you can change this notation like I did before. Change that notation to a folder. So plus, make it folder, title it, you know, just put whatever you want in there. And just tapped on something funky. And then just drag it up to wherever you want it. And then you'll see again that just dragging until that vertical line appears associates whatever you have with a particular folder. So now you have these, it's a lot more organized. You have these folders that this will give you the area under the curve, depending on an A value and a B value. All right. This will spit out the other way, where it's giving you, oh, I don't need this alpha, where it's giving you the z-score corresponding with a particular area. All right. And then the last one is to get the x value, you know, when you're given a mu and a sigma. So it's all relying on the z that you came up with before, but it'll spit out that value for you as well. So it's basically writing little programs for yourself to do the work for you. All right. So you do it the one time, save so you don't forget. Save so you don't forget to save. It's kind of a weird thing to think about, but it is what it is. But now you have this as a resource available to you forever. All right. Or at least as long as Desmos exists. So next up is the central limit theorem, and we have some problems associated with the central limit theorem. It's pretty interesting stuff. The last tech assignment dealt with the central limit theorem, so you got a little taste of it, but it definitely did not kind of get at all of the concepts associated with the central limit theorem. And the other thing to keep in mind is just because you completed an activity, it's like a lab in a science class. You complete the lab and it's like, okay, so now you know everything there is to know about light, you know, light waves and light particles. And it's like, well, no, I completed a lab. I did all the steps. I lit stuff on fire. It doesn't mean I learned what I was supposed to have learned. So here is where we try to get at what you should have learned from that tech assignment, which is kind of old now, but it's still meaningful. All right. So I'm going to actually jump right into the example at the bottom here, because I think, I mean, I don't think it's unfair to say this. If you read through this entire explanation, which I got from some textbook a long time ago, it only makes things worse. Like most of the time when you read a definition, when you read an explanation, it's supposed to make things better. This seems to actually do the opposite of that. Now, if I give you a good explanation, a good, like, relatable explanation of what the central limit theorem is, you'll walk away being like, okay, I think I get it. But then you read this explanation that's written here that came from a textbook, and you say, okay, that just undid all the learning that I gained from the hands-on stuff. So what I would say is I wouldn't even really bother reading this too much, except to say that these are two very important rules that we're going to come back to repeatedly, right? But let's see this whole thing in action. And we start off with a small case because when you did the tech assignment, we had more complicated data sets, but that's because we had tech. to work with. Here, we're not doing with text, so we're going to have a nice, simple data set to work off of. All right, so the population consists of only the numbers 1, 2, 3, and 4. All right, so I am defining a population as just the numbers 1, 2, 3, and 4. I can do that. You can define a population to be whatever you want. All right, so, and that's the thing. Statistics is very wishy-washy. We take a lot of liberties when it comes to statistics, which is why people are able to fool lots and lots of people using statistics, because there's so many different ways that you can interpret. There's so many different ways that you can develop arguments based off of statistical techniques. Right. So, for example, we have the population of the human race, right? But I can define a population as anybody who's related to me. That's what I designated as the population, right? In which case, I wouldn't call that a sample. I would call that a population, and I would do all the statistical values. Well, it wouldn't be statistics; it would be parameters. But I would use all the metrics associated with populations. Right, so we're going to find mu and sigma here. I'm going to open a new, you know what, I'll do it in here. The good thing about the Desmos calculator is it always reverts to the previously saved form unless you decide to save any kind of edits that you made. So if you have a version that you like, use it, but then don't hit save, or save it as a new file. All right, so I'm going to insert a table here consisting of just the numbers 1, 2, 3, and 4. All right. From there, I can get the population mean and the population standard deviation. So functions, stats, the mean, whether it's population or a sample, is always computed the same way. X1, 2.5. The standard deviation. Functions. This time I want population standard deviation. So ST dev P. All right, so X1, it gives me this funky number, which approximates out to 1.118. All right, so that's population mean, population standard deviation. All right, so if you want, again, when you're organizing your work and thinking in terms of a test, use the little note feature. The following is related to a population, or this is question 1, part B, or something like that. Whatever, just designate it any way that makes sense. All right. So now what we're going to do is list all possible samples of size 2 from this population. All right. So we have samples, and those samples are only going to be of size 2. So this is equivalent to, like when we had the deck of cards, all those different probability examples. If you have a deck of cards and I say, what's the probability of getting a king and then another king with or without replacement? You have your cards that are all available. You're randomly selecting from that set of cards. Well, that's all I'm doing here, except my cards are limited to just the numbers 1, 2, 3, and 4. Right. So I'm going to draw 2 cards. What could those 2 cards be? Allowing for repetition, that's the thing. Allowing for with replacement. So I'm not drawing the 2 cards at the same time. I'm drawing a card. I'm using kind of weird terminology here. When I say drawing a card, I'm selecting a card from the set. All right. So I'm withdrawing a card from the set. So I have the numbers 1, 2, 3, or 4. Let's say I get the number 2. I make a note of that, put the card back in the deck, shuffle it all up, and then select another card at random. All right. So what this is actually a sample space. So this is going to be kind of weird in terms of the terminology. Sample space of samples. So it's a sample of samples. sample space of samples. So our possibilities, I could get the number 1 and I could get the number 1 again. I could get the number 1 and I can get the number 2. I can get the number 1, I can get the number 3. I can get the number 1 and I can get the number 4. Right? That's one possible scenario. I could get the number 2 followed by the number 1. I can get the number 2 followed by the number 2, 2 followed by 3, 2 followed by 4. We'll move over to another column here. I can get 3 followed by 1, or too close, looks like a 31. 3 followed by 2, 3 followed by 3, 3 followed by 4. 4 followed by 1, 4 followed by 2, 4 followed by 3, and 4 followed by 4. Okay. So what I want to do here is I want to find the average, or so I want to find the mean of each of these samples. All right. So I'm going to find the average of the numbers 1 and 1. You know, then 1 and 2, then 1 and 3, and so on. Five years later. I gotta say, when I first started teaching this course, aside from like having archaic word problems, I also never actually finished the curriculum, at least in the first like decade of teaching this course, because there was just so much material and we had to do it all by hand. So to have the technology to do a lot of this stuff, even something as simple as this copy paste job here, it just makes things a lot easier. Now you might look at it and say, oh, that sounds great. We're not going to finish the curriculum. You want to finish the curriculum because a lot of the easy stuff is at the end. So anyway, average of 1 and 1, 1. You know, add them up and divide by 2. 1.5, 2, 2.5. 1.5. We're just splitting the difference between the two numbers, really. So 2, 2.5, 3, 2, 2.5, 3, 3.5, 2.5, 3, 3.5, and finally 4. All right. So what this is a list of all possible samples that you can get from the data set. All right. Which again consists of the numbers 1, 2, 3, and 4. So what I'm going to do in my list Y1 here is I'm just going to type all these values. All right. So that kind of sucks, but I'm going to do it anyway. And I always just remind myself, again, what I was saying a few minutes ago, is there was a time where you weren't typing this stuff in. There was nowhere to type it in. You were crunching these numbers by hand. All right, so barring any catastrophic error, it looks like I got all 16 values in there. So again, what I'm going to do is find the mean of these sample means. So each one of these ends up being a sample mean, right? So this is a list of sample means. All right, so we have our list of sample means. What we're going to do is find the mean of those sample means, and that's going to give us a value that should be equivalent to the population mean if we did it right. If we didn't do it right, then, well, I'll do what I always do. Stare at the screen with a vacant look on my face, trying to figure out where I screwed up. All right. So finding the mean. Function mean. This is in list Y1. Oh, look at that. It's equal to 2.5. So what this is, and so X bar is what we use to represent a sample mean. So X bar. So what we want is the mean, the population mean, because it's all, this is a sample space. This is all possible samples of size 2. So I wanted the mean of those sample means, which ends up being 2.5. I also want the standard deviation of those sample means. So the population standard deviation is ST dev P of Y1. And we get about 0.791. All right. So there is a relationship, and that's kind of what we're after here. So we look at those two rules, those two formulas that I said to highlight. That I said don't read anything else, just read those. Mu sub X bar and mu are the same. That's what one of the rules tells us. All right, my equal sign here is bothering me. According to this, that ended up being true. Wonderful. All right, so yeah, I put a little check mark next to that. We have verified this relationship. The other thing is that sigma sub X bar should be equal to sigma divided by the square root of n. All right, so sigma sub X bar, I'll just kind of jot it down over here, should be equal to sigma over the square root of n. So sigma, we determined earlier, was about 1.118. Square root of n represents the individual sample size. So this is the size of each sample. So in this case, square root of 2. All right. So if we did our computations correctly, then what we got for sigma right up over here, that 1.118, should be equal to divided by the square root of n, should be equal to 0.791 approximately. So what I'm going to do is I'm going to call this, I'm going to set this equal to capital S, and I'll just add it to the list of things to fix later on. That's really a sigma. So if I take my capital S and divide it by the square root of n, no, it won't let me. All right, well, I wanted to use the most exact decimal, but alas, it is not meant to be. So I'll just type it out the old-fashioned way, 1.118033. You don't have to put the whole decimal in. I just want to have that aha moment. 339.8875 divided by the square root of 2. And so you take a look at this and compare it to the standard deviation for the sample means. And you see that it's exactly the same decimal, right? So what that tells me is that we don't need to do this whole process of listing out all the samples, finding the average of each sample, then finding the mean and standard deviation of all those averages in order to determine what the mean and standard deviation ought to be for a sampling distribution, right? So all we need to know is that mu sub x bar is going to be equal to mu, and sigma sub x bar is going to be equal to sigma over the square root of that, right? Now, some of the benefits of the central limit theorem is it allows for distributions that are not necessarily normal to be converted into distributions that are normal, right? So what we're looking at here is a uniform distribution. The number 1, 2, 3, and 4 all occur equally, or equally, period, right? But if I were to create the graph of, and I think, let me see here, I might be thinking of a different function. Histogram, y1. Get a little display here. So this is not exactly a normal distribution. It's definitely not even close to a normal distribution, but that's because of the bin width that I selected here, right? So if I went by half units, it definitely looks a lot more like a normal distribution. And I can play around with the axis values. So let's say go from 0 to 5. It looks a lot better, right? So that looks an awful lot like a normal distribution. They have those extra points that are kind of floating out there in the middle of nowhere, but that's all right. Then I could also graph, a histogram for x1, and you can see that that's a uniform distribution, right? Uniform being they have the same height, right, throughout. So that's a pretty significant benefit of the central limit theorem. It takes distributions that are not necessarily normal and normalizes them so that we can apply probability concepts related to what we were talking about before, the normal curve, to determine actual probabilities. All right, so it's kind of a workaround. The other way, or the other benefit of the central limit theorem is it allows us to work instead of individual by individual, it allows us to work group by group, right? So if I wanted to say, and it's a pretty classic example, if I wanted to say, what is my probability of getting an A in this class? It's a pretty reasonable question, right? Yeah, and we have the data to verify it. So maybe you come up with a 90% chance of getting a 90% or better. Sounds good. Pretty solid probability. But then that's a different question from an alternate possibility. What is the probability that a class average is in the A range, right? So let's say I have, this semester I'm teaching 8 classes, right? So 8 different classes. And I want to know, of those 8 classes, what's my probability that at least 2 of them, or half of them, or all of them would end up having a class average in the A range, right? So that's talking about the group as opposed to the individual, right? And so that's the power of the central limit theorem. It allows us to work group by group instead of individual by individual. Okay, so let's take a look at some examples on the next page. What I tried to do was create problems where here's the non-central limit theorem version, and here's the central limit theorem version, so that you can get a sense of what the differences are. One striking difference, hopefully, when you look at and compare numbers 1 and 2. In number 2, it says n is equal to 100. They don't give an n value in number 1, so that's your first key indicator. Another one, the score versus the mean score. All right. If you're having a mean score, we're not talking about an angry score. We're talking about a score corresponding with a group. All right. So that's something to be mindful of. That mean is corresponding with a group. That group implies, or the fact that there's a group there implies central limit theorem. So what do? Well, we do what we've always done. We get down to business. So we got the 143 and the 29. We want to know the probability that the score is above 140. All right, so this is an X value. So I'm going to need a Z. Again, X minus mu over sigma. So 140 minus 143 divided by 29. All right. So I don't really need this stuff anymore. So I'm just going to get rid of that. And if you want, you can create another folder where it computes z-scores for you based off of individual pieces of information. All right. So you could even say find, I'll do it as a folder, find z given x, for example. And so z equals, problem is, you start putting too many scripts in the same Desmos, there might be a conflict, but we'll see. It would be x minus mu over sigma. All right. But then you would just have to know to call back on a previous mu and sigma, 143 and 29, so we're good there. The thing is that since I already used the z, it's confused. So what I can do is I could just kind of get that out of there. And you know what? The x is a variable. Let me actually see something here. Let's make this value, v for value. Nah, it's having a hard time. But the idea is that you can try to make a program to allow it to work. S for score. I've already used S. Oh wait, no, I used capital. Bottom line is you can try to make it work. Right? Well, what I'm going to do is I'm just going to crunch it by hand. So we got this value, negative 0.103. All right, so here's 0, 1, 2, 3, negative 1, negative 2, negative 3. I need to go negative a smidge to the left of the y-axis. We're talking something, oh, that's not my vertical line draw tool. So this is z equals negative 0.103. Now, the score is above 140, right? So what they're asking us for, in effect, is the probability, let me get a thicker pen here, probability that x is bigger than 140. But that in turn means that z is bigger than negative 0.103. All right. So negative 0.103 is our magic value. So I can go back to my area under the curve. 0.103 is on my low end. On my high end, something really big. $10 is usually sufficient. I mean, it's always sufficient. So 0.541. All right, I expected something to be a little bit more than half, and I got something a little bit more than half. So that's good news. All right, so I did my 140 minus 143 over 29, and I just evaluated that. And you know, you could sketch it up a little bit, make it look nice. But that's what we were expecting to see, right? About 0.541. Now, in number 2, it's saying find the probability that the mean score is above 140, given all this stuff, right? So because of all that other information, we now know that it's a central limit theorem problem, which means that I need not mu, but mu sub x bar, but turns out that it's 143 anyway. Not sigma, but sigma sub x bar, which is sigma over root n, which in this case is 29 over root 100, so 2.9. Now, only subtle changes are going to happen, which is kind of weird to think about. I mean, we'll have a massively different looking answer, but the approach is going to be very, very similar to the point where it could get kind of confusing, you know, confusing in its simplicity, right? So we have this graph here, which amounted to, in number 1, a little bit more than 50%. I'm still going to have benchmarks of 0, -3, -2, -1, 1, 2, and 3. I need to know the probability that x bar is greater than 140. But I need to know the z-score that corresponds with that. So z is going to be not x minus mu, but x bar minus mu sub x bar over sigma sub x bar. All right. So I'm making slight adjustments to my z-score formula to allow for this to happen. So my x bar, that's the value that's given for the mean score, 140 minus 143 over, instead of 29, it's now 2.9. So slight adjustment here. It's 140 minus 143 over 2.9, which gives a z-score of negative 1.0345. All right, so that's our cutoff. That's what we're looking for. So instead of x bar being greater than 140, I'm looking for the probability that z is greater than negative 1.0345. Back to my calculator. I'm sliding this over. Well, it's not going to be precise, so I'll just type it in. Negative 1.0345. Then I can go look at the readout there, and it looks like it's about 0.85 now. All right. So approximately 0.850. So we had about a 30% probability jump, which is insane. In terms of the graph, negative 1.03 is going to be somewhere in this neighborhood. Four, 5. And we're still shading to the right. But you could see a lot more of the normal curve has been accounted for now. Right, a whole lot more. So it begs the question, and it's a very important question, how and why? Why did that happen? And it has everything to do with the grouping aspect of it, right? Because what we're talking about here is, you know, just, again, it's probability. So it's very difficult in a lot of cases to think of probability in terms of, you know, real world context. But if I tell you that the probability could be representing a number, so the number associated with probability could be just a number indicating how difficult it is to achieve something. So if I tell you, and you know, this is again related to the weights of women, so let's not focus on that, but like if I tell you that my goal is for a student, you know, like Tommy, I want Tommy to get an A in the class. So what's the probability that Tommy is going to get an A in the class? Right? Whatever it is. And in this case, let's say it's 0.541. Then the alternative to that would be, all right, I have 100 students. What's the probability that they're going to get an A in the class? Right? That's going to be a massively different probability, right? So if we think about it in the sense of, you know, how much harder is it to make that happen? So just think of it this way. If I want Tommy to get an A, let's say I'm a tutor, you know, like Tommy's in, you know, taking a stat class and I'm tutoring Tommy on the side. I can get Tommy to an A by dedicating a lot of time and resources to his success. But to get a group of 100 people to have an average that is an A, that's going to be a lot more challenging, right? So that's really what the central limit theorem is talking about. It's what's going on with the whole group, right? So once we take samples from a population and find averages within those samples and start averaging it all together, we start eliminating extreme values, which makes the data seem more tightly grouped, even though it's not necessarily the case. That impacts the probability significantly, right? But ultimately, we're looking for the group probability as opposed to the individual probability. So like number 3 is a combo problem. Just like numbers 1 and 2, the first part is not central limit theorem, the second part is. So math professors have IQs that are normally distributed with a mean of 125, a standard deviation of 1.2. So a reasonably, I was going to say high IQ, but like above average, but not too far above average, I guess. But a tight distribution. You know, 1.2 is a pretty small number for a standard deviation. One professor selected at random, find the probability that his IQ is greater than 127. All right, so this is my X value. So ultimately the question is, find the probability that X is greater than 127. And we know that mu is equal to 125 and sigma is equal to, what did I say, 1.2. We know that Z is equal to X minus mu over sigma, which in this case would correspond to 127 minus 125 over 1.2. So I can crunch those numbers. So it's 2 on the top, 2 divided by 1.2, about 1.67. I'll put that in fraction form, 5/3. So this translates to the probability that Z is greater than 5/3. So again, 0, 1, 2, 3 if you want. You don't have to label the whole thing up. Just label the center and then the part of the graph that needs to be labeled, 1.3-ish, or 1.6, sorry. That's a little bit more than halfway between 1 and 2. So Z is equal to 5/3, or 1.6 repeated if you like. And we want to know this area. So the cutoff on the low side would be 5/3, not 593, 5/3. All right. On the high side, something big, we're talking about 0.0478. All right. So we have a probability value that's less than 5%. So it's pretty unlikely, not unlikely, unusual is what I meant to say. All right, sounds good. So to find an individual professor, because basically what this problem is saying is that intelligence-wise, professors, math professors, are all kind of like in the same neighborhood. Their intelligence capacity is all like right around that 125 mark, and they're all kind of like in lockstep with one another. So if somebody's going to deviate from that, it's going to happen at a low probability. So the central limit theorem version of this is that now you have 75 professors, and we want their mean IQs to be greater than 127. All right, so this is saying that the probability that X bar is greater than 127, knowing that N is equal to 75. That's a different question, because if I'm telling you that it's pretty rare for an individual's IQ to deviate from the norm, then to get a group of 75 to have IQs that are going to deviate from the norm, that's going to be even rarer, right? Also, something else to consider. You can kind of look at this as a basis of comparison. So let's say historically, math professors have had IQs around 125 with the standard deviation of 1.2, and like I'm the dean at some school that thinks very highly of itself, right? And so what I might say is, all right, well, I think our math department, our math faculty is significantly brighter than your math faculty. So I think that my 75 teachers are significantly more intelligent than your 75 or 100 or 1,000 teachers, like nationwide, right? This kind of problem would lend itself towards that. If you think that a group deviates significantly from the norm, then this would kind of lead towards that conclusion. A nice application of something like this is if you're remediating a group of students, like you're a teacher and you're remediating a group of students, you think that the program you developed, or you could be like a coach, athletic coach, you could be a music teacher, an art teacher, whatever. You think whatever program you have is going to lead to results, and so if you can show that the outcomes don't just apply on a person by person basis, it applies for large groups at a time, then that's going to be a more meaningful conclusion, right? But in terms of the computation, there's really not much more to it, because like we did before, I need mu sub x bar, and I need sigma sub x bar. Mu sub x bar is the same as mu, which is in this case 125. Sigma sub x bar is sigma over the root of n, which in this case is 1.2 divided by the square root of 75. In the past, people have kind of gotten the impression that all you're doing is dividing by 10, because the previous example was dividing by 10 in order to get the sigma sub x bar. That only happened because n was equal to 100. So don't fall in love with particular outcomes. It all varies depending on the nature of the data. All right, so square root of 75. So we're looking at about 0.139. So I'm looking for, again, we have p x bar greater than 27. I need the z score corresponding with that. So z is going to be equal to x bar minus mu sub x bar over sigma sub x bar, which in this case is 127 minus 125 over about 0.139. So it's really 2 divided by this funky decimal. You can work with the rounded form though. So Z is, look at that, 14-ish, 388. I can't even shade this, right? This is 0, 1, 2, 3. 14's off the grid. I'm not even going to bother, right? So I'm looking at some value that's going to be so teensy tiny that it's not even going to fit on a normal curve, right? So this is going to amount to the probability that Z is greater than 14.388. Now, if I go to my area under the curve model, I type in the 14.388. Under normal distribution, you see I get that little hazard sign. It's telling me that there's an issue, and that's because my high bound is smaller than my low bound. So my B needs to be something a lot bigger, right? Because 10 is smaller than 14, and it's got to be a max. So I'll make it like 100. Play it safe. And then I look at my probability, and you can see that it is astronomically minuscule. So 3.0775 times 10 to the negative 47th power. Very small. It's so small that it's almost, I mean, you might as well just think of it as 0. That's how unlikely it is. Because this is point, then type out 46 zeros, then the 30775. All right, so very, very, very tiny. All right. So what this does is it gives us very strong evidence that you're not going to find 75 math professors, a group whose average IQ is more than 127. Right. So now, whether or not 127 is considered to be, a high number, I forget. I know it used to be 110. 100 is the mean, like average IQ, and 10 was the standard deviation. So anything anything over 120 would be unusually high. So, it doesn't always play out that way anymore, but that was the old school way of thinking about it. Now it's a little bit more complicated, but that's generally the idea. So what I'm going to ask you to do, I'm just going to put some stars on numbers 4 and 5. So give those a shot for homework, and not homework, you know what I mean. Try those for next class. We'll do number 6 together. So we'll start off class on Wednesday doing numbers 4 and 5, but we'll also do number 6. And then we're going to talk about designing a study. So what I'd also like you to do, and there's really not much to it, what I'd like you to do is read through the definitions on page 55. So all of this stuff, it's not a lot. I'm not a big fan of making people read stuff, like in general. Because if I make people read stuff, then they turn around and want me to read stuff. So that's not a good thing. All of 56. Aw. You get the idea, though. 57. Oh my God, is this guy crazy? No, seriously, it goes quick. I'm not asking you to memorize anything. I'm just asking you to have read this over by the time we sit down for class next time. All right, because all right, well, you get the idea. It makes things a lot easier if you have some experience with this material before I start blabbing on about it. All right, so very, very important. If I can, I'll fix that later. And then, just keep reading through page 59. After that, it's not going to make any sense anymore. If it makes sense up until this point, that's great, but it doesn't always play out that way. But this is the different types of samples. And you would just finish up over here because the last little bit we have to talk about together. All right, so just asking you to do some reading, nothing too crazy. Honestly, it's like, it seems like I'm asking you to read a lot, but it's like 5 minutes worth of reading. Right, so it's nothing too crazy. And I'll fix this highlighting crap that I for some reason decided to get fixated on. So that's where we're going to leave it for tonight. If you have any questions, stick around. Otherwise, have a wonderful evening, and I will see you all on Wednesday.
All right. Thanks.